For decades, the traditional Linux model has followed a simple philosophy. You install a distribution. You install packages on top of it, and over time your system evolves. You update libraries, tweak configuration files, add repositories, remove software, experiment, break things, fix them, and repeat. This flexibility has always been one of Linux's greatest strengths. But it has also been one of its biggest weaknesses. The more a system changes over time, the harder it becomes to guarantee stability, reproducibility, and reliability. And that's exactly where immutable Linux distributions enter the conversation, not as a niche experiment, but as a fundamental shift in how we think about operating systems. Immutable Linux distros flip the traditional model on its head. Instead of allowing the base system to be modified freely, they treat the operating system as a read-only atomic image. The core system is locked down. You don't casually replace system files. You don't gradually accumulate configuration drift. Instead, updates arrive as complete, tested snapshots. If something goes wrong, you roll back to a previous working state. Instantly, cleanly, predictably. This approach feels radically different at first, but the longer you examine it, the more it starts to look like the natural evolution of desktop and server computing. To understand why immutable distros are so compelling, you have to understand the problem they're solving. Traditional Linux systems are mutable by default. Over time, the package manager modifies thousands of files across the file system. Dependencies get upgraded. Some packages lag behind. Configuration files are edited manually. External repositories introduce unpredictable combinations of libraries. Eventually, the system becomes unique as snowflake. And while that uniqueness reflects user freedom, it also introduces fragility. Reproducing that exact state on another machine becomes nearly impossible. Debugging issues becomes harder because no two systems are truly identical. Immutable systems aim to eliminate this drift. The base operating system becomes a stable, versioned image. When you update, you're not patching individual components one by one. You're switching to a new system image that has been built, tested, and validated as a whole. This is similar to how modern smartphones operate. On platforms like Android or iOS, users don't manually replace system libraries. They receive complete updates. The integrity of the base system is preserved. Linux immutable distros borrow that philosophy and apply it to general-purpose computing. One of the most powerful advantages of immutability is atomic updates. In a traditional distro, if an update fails halfway through due to power loss or a broken dependency, you might end up with a partially updated system. Recovery can be painful. In an immutable system, updates are applied as complete images. Either the new version is successfully deployed and activated, or the system continues running the previous version. There is no in-between state. This dramatically reduces the risk of catastrophic system failure during updates. Rollback capability is equally transformative. Imagine installing an update, rebooting, and discovering that your graphics driver is broken or a critical application no longer launches. On a traditional system, you might scramble to downgrade packages manually, search forums, or restore from backups. On an immutable distro, you simply select the previous system version at boot. Within seconds, you're back to a known good state. That level of safety encourages users to update more frequently, which in turn improves security and long-term stability. Security is another core reason immutable distros represent the future. When the root file system is read-only, the attack surface shrinks dramatically. Malware that relies on modifying system binaries or injecting persistent changes into core directories faces significant barriers. Combined with containerization and sandboxed applications, immutability creates layered defense by design. Even if a user-level application is compromised, altering the base system becomes much harder. This security model aligns perfectly with modern software distribution methods. Over the last few years, containerization has become mainstream. Tools like Docker normalized the idea that applications should run in isolated environments with their dependencies bundled. On the desktop, sandbox packaging formats such as Flatpak reinforce that separation. Instead of polluting the base system with conflicting libraries, applications run independently. Immutable distros embrace this model fully. The base OS provides a stable foundation, and applications live in containers or sandboxed layers above it. One prominent example of this approach is Fedora Silverblue. Silverblue treats the operating system as an image managed by RPM-Ostry. Users don't traditionally install packages into the base system. Instead, they layer applications or use Flatpak for desktop software. The result is a system that feels stable and predictable, yet still flexible when needed. Another example is openSUSE MicroOS, which focuses on transactional updates and automatic rollbacks. On the declarative side, NixOS takes reproducibility even further by defining the entire system configuration in code, ensuring identical deployments across machines. What makes these projects especially significant is that they're not fringe experiments anymore. They are backed by major communities and organizations. Enterprise environments increasingly demand reliability and reproducibility. Cloud infrastructure thrives on immutability. In fact, the cloud-native ecosystem is built on immutable principles. Servers are often treated as disposable units. Instead of patching a live machine, administrators deploy a new image and replace the old one. This immutable infrastructure philosophy has proven its value at scale. As the boundary between desktop and cloud blurs, these principles begin migrating to personal computing. Developers now rely heavily on containers, virtual environments, and reproducible builds. An immutable desktop fits seamlessly into this workflow. You can keep your base system clean and consistent while spinning up development environments in containers. If something breaks inside a container, you delete and recreate it. If something breaks at the system level, you roll back. Another reason immutable distros are gaining traction is cognitive simplicity. Traditional Linux offers freedom, but that freedom can overwhelm users, especially newcomers. Multiple package managers, conflicting repositories, manual configuration tweaks, it's powerful but complex. Immutable systems reduce the number of moving parts in the base OS. There's one tested image. There's a clear update path. There's a safety net. That predictability lowers the mental overhead of maintaining a system. Critics sometimes argue that immutability restricts power users. But in practice, immutable distros provide structured flexibility rather than removing flexibility entirely. Tools like Toolbox or Distrobox allow users to create mutable environments inside containers. You can experiment freely without jeopardizing the base system. It's a shift from everything is mutable to mutation happens in controlled layers. That architectural clarity benefits both beginners and experts. The performance implications are also worth considering. Atomic updates and snapshot-based file systems often leverage technologies like BTRFs, enables efficient storage of multiple system states. You can maintain previous versions without duplicating every file. This efficiency makes rollbacks practical without consuming excessive disk space. Over time, file systems designed with snapshots in mind become more integrated with the immutable model. From a development standpoint, immutability improves testing and quality assurance. When the operating system is built as a cohesive image, maintainers can test it as a single unit. They don't have to account for every possible combination of partially upgraded packages. This reduces unpredictable edge cases. It also accelerates innovation because maintainers can focus on improving the system image rather than troubleshooting fragmented upgrade paths. There's also a psychological shift happening in how users view their operating systems. Historically, many Linux enthusiasts enjoyed customizing the core system endlessly. Editing configuration files was part of the culture. But modern computing habits are different. People expect reliability similar to appliances. They want their system to boot, update, and run without drama. Immutability aligns Linux with that expectation without sacrificing its open nature. Consider how operating systems like Chrome OS operate. Chrome OS uses a read-only root file system with automatic updates and seamless rollbacks. Users rarely think about system maintenance. That simplicity has been a key factor in its adoption in education and enterprise environments. Immutable Linux distros adopt similar principles while retaining full Linux flexibility and openness. In enterprise contexts, immutability reduces downtime and operational risk. When systems are predictable, scaling becomes easier. Deploying 10 machines with identical configurations becomes trivial if they're based on the same image. Troubleshooting becomes systematic because environments are consistent. Configuration drift, a notorious problem in system administration, virtually disappears when the base image is immutable. There's also an environmental benefit in treating systems as images. Reproducibility means fewer wasted hours debugging inconsistent states. Automated testing pipelines can verify system images before release. Continuous integration systems can build and validate images in predictable ways. The entire lifecycle of the operating system becomes more modern and aligned with DevOps practices. For content creators and power users, immutability offers peace of mind. You can experiment with themes, containers, and development tools, knowing that the core system remains untouched. If a risky experiment goes wrong, recovery is straightforward. That safety encourages creativity rather than discouraging it. Another critical dimension is long-term maintainability. Traditional systems often degrade subtly over time. Small configuration tweaks accumulate, old dependencies linger, obsolete packages remain installed. An immutable system resists that entropy. The base remains clean with every update. It's like refreshing the foundation regularly while preserving user data and settings. Even hardware support benefits indirectly. When updates are delivered as tested images, compatibility with kernels and drivers can be validated holistically. This reduces surprises after updates. Combined with rollback functionality, hardware regressions become less catastrophic. The educational impact should not be underestimated either. Immutable distros introduce users to modern infrastructure concepts naturally. By interacting with layered systems, containers, and declarative configurations, users gain skills relevant to cloud computing and DevOps environments. The desktop becomes a training ground for industry practices. Of course, immutability is not a silver bullet. It requires a shift in mindset. Users accustomed to directly modifying system files must adapt to layering or container-based workflows. Documentation and onboarding must improve to ease that transition. But as tooling matures, these friction points diminish. What's remarkable is how quickly the ecosystem is evolving. More distributions are experimenting with immutable variants. Major desktop environments are improving support for sandboxed applications. File system technologies are advancing. The momentum suggests that immutability is not a passing trend, but a structural transformation. Ultimately, immutable Linux distros represent a convergence of reliability, security, reproducibility, and modern software practices. They preserve Linux's core strengths, openness, customization, community, while addressing long-standing pain points around stability and maintenance. They bring desktop Linux closer to the resilience of mobile operating systems and the scalability of cloud infrastructure. The future of computing is increasingly image-based, containerized, and declarative. Infrastructure is defined as code. Systems are rebuilt rather than patched in place. Updates are atomic. Rollbacks are instant. Security is layered. Immutable Linux distros embody all of these principles in a cohesive form. As users demand systems that just work without sacrificing control, immutability provides a compelling answer. It doesn't eliminate freedom, it reorganizes it. The base becomes stable and trustworthy. Customization moves to controlled layers. Recovery becomes trivial. Updates become fearless. In that sense, immutable Linux distros are not merely another flavor of Linux. They are a reimagining of what a Linux system can be in a world shaped by cloud-native architecture and security-first design. They are a bridge between the hacker ethos of the past and the reliability expectations of the future. And as the ecosystem continues to mature, it becomes increasingly clear that immutability isn't just an experiment. It's the direction Linux has been moving toward all along.